This is part 2 of two-dimensional motion, in which we'll talk about horizontal projectiles. We have talked about resolving vectors into their components, and we have talked about taking the components and putting them back together to get the resultant. And now we're going to use the vector analysis that we've learned how to do. Velocity has two components. Velocity has an x component and it has a y component. In any projectile problem, the x component remains constant while the y component is accelerated. The y component, gravitational acceleration, is in the vertical direction, and so the y component will change, increase or decrease, depending on the direction it's moving. The x component stays constant the whole time. What's special about horizontal projectiles is that they start with only horizontal velocity. The y component, which at the beginning, which we'll call Vy0, the initial y component of the velocity, is 0. But as soon as it is released, it begins to fall. Projectiles are a combination of free fall problems and constant motion problems. So if you look at this, at the red dots, that's the actual projectile. The projectile travels horizontally the same distance in the same amount of time. So if these dots were 1 second apart, the red dot travels exactly the same horizontal distance in each second. So Vx is constant. The x component doesn't change. The y component, however, if you look at the blue dot, it looks just like what we saw when we did free fall. It starts with a 0 velocity and it gets a little faster and travels a small distance, and then it gets a little faster and travels a larger distance. And in each subsequent time interval, it travels a greater distance because it's accelerated. So when we have projectiles, whether they're horizontal or not horizontal, we have to consider both dimensions separately. The time it takes to fall depends on how high it is. How far it goes during that time will depend on how large the x component of the velocity is. The special thing, again, about horizontal motion problems is they're a little bit simpler because the initial y velocity, the y velocity at the beginning, is 0. You will never see me write Vx0. I'll erase it because you just saw me write it, because I don't need an x0 or Vx0 because Vx stays constant the whole time. So let's try to remember what the equations were that we used for free fall problems and for constant velocity problems. Well, we'll start with constant velocity problems because that's simpler. In Chapter 2, when we did non-accelerated motion, we just had objects moving with a constant velocity or with an average velocity, we said that the average velocity was equal to distance over time. We're going to use variables now that are relevant to the problems that we're solving. And so we will say the x component of the velocity is equal to the x component of the distance, or that's also called the range. The distance that from the directly beneath the starting point to the ending point is x, and that is our range. The x component of the velocity is the x distance, the horizontal distance, divided by time. Now there are a lot of equations for free fall. Y equals y0 plus Vy0t plus 1/2 gt squared. Now think about the signs on g. Sometimes we'll use positive and sometimes we'll use negative. If our initial y velocity is positive, then we'll need to use a negative value for g. If, like in a case of horizontal projectiles, we can let down be positive, then we'll let g be positive, just like we've always done. The other equations that we used, the y velocity at any time will be the initial y velocity plus acceleration times time. Now remember, g might be plus or minus depending on the direction of the initial velocity. And the third equation that we may find use for is that Vy final squared equals Vy0 squared plus 2gy. Okay, we've written this before. You might remember it. Vf squared equals vi squared plus 2ad. That was the general equation. I'm going to erase that in just a second because it doesn't have the variables in it that are relevant to what we're doing, but I don't want you to think this is a new equation. Vf squared. Now, the only accelerated velocity is our y velocity, not our x. So I replace that with vyf squared, the y component, the final y component of the velocity squared, equals the initial y component of the velocity squared, vi squared, plus 2gy. 2a, well, it's accelerated by gravitational acceleration. And instead of d, I use the y component of the motion, the height or the y distance that the object has traveled. So those are the equations that we can use. The good news is, in horizontal motion problems, the initial y component of the velocity is 0, and the initial y position is 0. We're going to consider this 0, and then it moves down to y, just like we would consider this 0. It'll move out to x. So these two things are 0, which means that that equation can be reduced to y equals 1/2 gt squared. Now, we won't do this in non-horizontal projectile problems. What we'll normally use this for is for finding time. Now, can you do the algebraic manipulation it takes to solve for t? Well, let's do this together. In order to isolate the t, we need to multiply both sides by 2. Because if I multiply by 2 over here, the 2 and the 1/2 will cancel, right? So I'll end up with a 2y over here. And then, okay, the 1/2's gone. I need to get rid of the g. Well, if I divide both sides by g, the g in the top and the g in the bottom will cancel, and I'll have 2y over g on this side. That'll be t squared. Now I need t. Time equals the square root of 2y over g. This works as long as these two initial conditions apply, that your initial velocity is 0 and that your initial position is 0. But this equation and this equation are the two that we're going to use most as we solve horizontal projectile problems. So let's do some problem solving. There are really two types. If I have an object thrown horizontally off a cliff, and that cliff has a height of y, and the object lands a distance x away from the base of the cliff or tower or whatever, you will know the height of the cliff. You will either know the x component of the velocity and you'll have to find the distance, or you'll know the distance and you'll have to find the x component of the velocity. So one of these will be given and the other you'll have to find. Suppose an object is thrown with an initial horizontal velocity of 10 meters per second off of a cliff that is 80 meters high. How far from the base, so we're looking for x, how far from the base of the cliff will it land? Well, if we're trying to find x, well, let's find an equation that has x. The only equation we have that has x in it is this. Now I want to remind you, this is not a variable. This is a subscript describing the velocity. This is a variable. So I don't want Vx. I know it. I need x. So let's rearrange this equation. X equals Vx times time. Well, I know Vx. I don't know time. So I need to do some stuff with the y component, those y equations, to find time. Then I'll plug it back in here, and I'll be able to find my distance. So that equation that we derived, time equals the square root of 2y over g. Time equals the square root of 2 times 80 over, I'm going to use g equals 10. 2 times 80 is 160. 160 over 10 is 16. And the square root of 16 equals 4 seconds. Now I'm going to take that 4 seconds I'm going to plug it in over here, and I get 10 meters per second times 4 seconds is 40 meters, and we have found the distance. Okay, so we have to separate the vertical stuff from the horizontal stuff, and the one thing they have in common is time. In the time it takes to fall 80 meters, it traveled horizontally 40 meters. And so the time is the one thing that links the vertical motion stuff and the horizontal motion stuff. Let's do one more example. A motorcyclist drives off a cliff. This is not a dark and dreary problem. He wants to drive off a cliff. He's like Evel Knievel or something. So a motorcyclist drives off a cliff that is 20 meters high. So y is 20 meters, and lands 40 meters, all happy and healthy, from the base of the cliff. How fast was he going? So what we're looking for in this case is the horizontal component of the velocity, Vx. So write an equation for it. Vx equals x over t. Do we know x? Yes, we do. It's 40. Do we know time? No. So we have to come over here and do vertical stuff. Time is the square root of 2y over g. That's the square root of 2 times 20 over 10. Be careful when you're writing these. Make sure that your radical comes down so that you're not going to mistakenly only take the square root of the 2y part. All three of these values is under the radical. 2 times 20 is 40, and 40 over 10 is 4, and the square root of 4 is 2 seconds. So now we'll take that 2 seconds, plug it in over here. 40 divided by 2, Vx is 20 meters per second. Okay, hopefully you've taken good notes so that when you do practice problems, you can use your notes as a template for solving other horizontal motion problems. Bear in mind, the x component is constant, the y component is accelerated.